What is up, young chemists? Mr. Rosen here. Hope you are doing well, hanging in there. The focus of this video is Lewis structures and how to draw them. We're going to go through the steps and then work some example problems. But a Lewis structure is a way to represent a molecule, a two-dimensional way to represent a molecule, drawing a molecule on the page. So, as it says here at the top, Lewis structures are a visual representation of a molecule and how atoms are bonded to other atoms. So these are the steps, and we're going to just sort of read through them, and then doing example problems is really the best practice, or the best thing to learn this. So, steps for drawing a Lewis structure. Step 1. Add up the total number of valence electrons in the molecule. So that's the same as the group number if your periodic table is using the A's. So we're just going to have 1 through 8A. The periodic table I have goes 1 through 18, but I'll talk us through it. Step 2, place carbon, if you have carbon, or the least electronegative atom at the center of the structure and arrange the other atoms around it. Okay, so on the periodic table, the bottom left corner of the periodic table has the lowest electronegativity values, and the upper right corner, okay, this is with the exception of the noble gases, has the highest electronegativity. So fluorine has the highest electronegativity. And electronegativity is a measure of how strongly an atom will pull shared electrons towards itself. So if let's say two things were bonding, like if, for example, if hydrogen was bonding with fluorine, this line represents two shared electrons. There are electrons in the space between these two atoms. This hydrogen is going to exert some pull on the electrons. This fluorine is also going to exert some pull on these shared electrons. Electronegativity is a measure of how strongly the atom pulls shared electrons towards itself. Fluorine is the most electronegative element, so the electrons will be pulled more towards the fluorine side of this. Okay, so step 3, connect atoms using single bonds, and a single bond represents 2 electrons. Right? So it says subtract 2 electrons from the total number of valence electrons for each single bond that you draw. You can then arrange any remaining valence electrons to fulfill all duets. Duet means 2, or octet, which means 8. So hydrogen follows the duet rule. Actually, that's written right here. Hydrogen follows the duet rule, meaning that it has a maximum of 2 electrons, which is the same as a single bond. So hydrogen will only form single bonds. You will never have a double bonded hydrogen or a triple bonded hydrogen. You will also never have anything bonded through hydrogen, right? Like I couldn't have an F bonded to an H, which is bonded to another F, because that would have 2 bonds on the hydrogen. Hydrogen only forms one single bond, so it's always sort of periphery or on the outside of the molecule. Other elements follow the octet rule, and there are exceptions to the octet rule, but we're not going to cover any exceptions. Okay, let's do some examples, and you can see how I'll work through these steps, and then we will do even more practice together. So, example number 1. What is the Lewis structure for CF4? So step 1, add up the total number of valence electrons. Now to do this, you can look on your periodic table, and the number of valence electrons will be the same as the group number. Okay, now on my periodic table over here, it's pretty easy. This is column 1, this is column 2. These have 1 valence electron, these have 2 valence electrons. Over on this side, your periodic table will probably have 3A, 4A, 5A, 6A, 7A, and 8A. And they might even be written in Roman numerals. So carbon right here is in column 4A. It has 4 valence electrons. So carbon has 4 valence electrons. And fluorine right here is in column 7A. So it has 7 valence electrons. So carbon has 4. These are valence electrons, which means outermost electrons. And fluorine has 7. It's not total number of electrons, it's valence electrons, outermost electrons. So it says place carbon, or the least electronegative atom, at the center of the structure and arrange the other atoms around it. So we actually do have a carbon. So I'm going to put a carbon here, and then I'm going to put the other elements around it. And we're going to have them get as far apart as possible. And drawing this flat on the page, I'm going to draw an F, an F, and F, and an F. Okay. Step 3, connect the atoms using single bonds. So I'm going to draw a single bond here, a single bond here, a single bond here, and a single bond here. Each of these bonds is 2 valence electrons. So that's 2 valence electrons, that's 2 valence electrons, that's 2 valence electrons, that's 2 valence electrons. Now, in step 1, it says add up the total number of valence electrons, and this is a key idea. Carbon has 4 and fluorine has 7, but our total is not 11 because look, we have 4 carbons. So we have 4 fluorines. If we have 4 fluorines, we need to multiply this by 4, which gives us 28 valence electrons. Adding up the total, it's 4 plus 28. Okay, so 4 plus 28 is 32 valence electrons. So that's our total number of valence electrons. Now, each of these is 2 valence electrons. So of the 32, in making this structure, we have now used up 2, 4, 6, 8. We've used up 8 of these. So the next step is going to have us subtract 8 valence electrons from the total, which is 32. So step 4, it says subtract 2 electrons from the total number of valence electrons for each single bond drawn. So the total number of valence electrons was 32 electrons, and the number of single bonds was 4, and 2 each is 8. So we're going to subtract that and have 24 electrons remaining. And this says arrange any remaining valence electrons in order to fulfill all octets and duets. Now we don't have any hydrogen, so we're not gonna have any duets. It's just gonna be octets. So we have carbon, and it's single bonded to fluorine on 4 sides. Just redrawing what I had on the last page. And we have 24 electrons left. Now, if you look at carbon, carbon has 2, 4, 6, 8 electrons on it. So it has a full octet, so it's done. But this fluorine only has 2. So I'm going to add 2, 4, 6 electrons to this fluorine. So now this fluorine has 2, 4, 6, 8. And you can see that we have 24 electrons and there are 4 fluorines. So we could do this, put 6 on each fluorine, and 6 times 4 is 24. It's going to work out perfectly. So I'm putting in the lone pairs. Now if you look at this, fluorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All the fluorines have 8, and the carbon has 2, 4, 6, 8. So they all have octets. And the total number of valence electrons has to be 32. So we can check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Ta-da! Valid Lewis structure. All of our octets are fulfilled, and we have the correct number of total valence electrons. Now, this little notice is just explaining what I just said, but in words. It says to check your work, make sure all atoms have a full octet or duet if there's hydrogen, and then you also want to make sure that the total number of valence electrons is the correct number of electrons. So here will be our first 4 practice problems. If you want to pause the video and draw the correct Lewis structure for these 4, and then we will work through and get to the answers. Okay, here we go. Step 1, count the total number of valence electrons. Now, we just had a problem with fluorine, and fluorine has 7 valence electrons, and there are 2 of them. So 7 times 2 is 14 total valence electrons, okay? So for each of these problems, you should have the total number of valence electrons right now. We have 2 fluorines, so we're going to draw an F, and then we're going to draw another F. Now, it's a molecule, so that means that these are going to be connected to each other. So start by connecting them with a single bond. That bond uses up 2 of the 14. So 14 minus 2 is 12. So we have 12 electrons remaining. You now need to arrange those 12 electrons so that this fluorine has an octet and this fluorine has an octet. Now 12 divided by 2 is 6. So we can actually just put 6 on this side and 6 on this side. And if you look, fluorine has 2, 4, 6, 8, and fluorine has 2, 4, 6, 8. They both have 8, and the total is 2, 4, 6, 8, 10, 12, 14. Valid Lewis structure. Okay, I'm sorry this F is so ugly. Next question. HI. Hydrogen is in column 1 on the periodic table, so it has a 1 electron. Iodine is in column 7A of the periodic table. It's the second from the right column, 7A. It's actually just a couple elements, 2 elements down from fluorine. This has 7 electrons. So 1 plus 7 is 8 total valence electrons. And there's just 1 of each, so that's it. So we're going to have H, and then we're going to have I. We're going to connect them with a single bond. That uses up 2 of these, and there are 6 electrons left. Now, you need to make sure that you have your octets and duets fulfilled. Hydrogen follows the duet rule. So this single bond gives hydrogen 2 electrons. So it's done. We don't need to put any more electrons on it. It has a full valence shell. these 6 electrons are all going to go on the iodine. So now the iodine has 2, 4, 6, 8. The hydrogen has 2, so they both have their octets and duets fulfilled. And the total number is 2, 4, 6, 8. This is your valid Lewis structure. Next up, GeH4. Ge is a couple elements underneath carbon, so it's in column 4A. Ge has 4 valence electrons. Hydrogen has 1 valence electron because it's in column 1A, and that we have 4 of, so 1 times 4. It's going to be 4 plus 4, so that gives you 8 electrons. So we're going to put Ge at the center, and the reason we're putting Ge at the center here is because H will never be at the center. It's always going to be on the outside, and the reason is it can only form 1 bond, right? If we put H at the center, then that would mean multiple things are connected to it, which is never going to happen. So we're now going to connect them using single bonds. Single bond, single bond, single bond, single bond. Each single bond counts for 2 electrons. 2, 4, 6, 8. So we have used up all 8. And now let's see. Well, each hydrogen has 2, right? 2, 2, 2, 2. So the hydrogens are fine, and Ge has 2, 4, 6, 8. Octets are fulfilled, duets are fulfilled, and the correct number is 8. That's your valid Lewis structure. That's it. How about H2O? So as we just said, hydrogen has 1 electron, and there are 2 hydrogens. And then oxygen is in column 6A on the periodic table. It's this third one from the right. It has 6 electrons. So 2 plus 6, again, is 8 electrons total. So we have 8 valence electrons total. We're going to put oxygen, and then we're going to put hydrogens on opposite sides, connect them using single bonds. That's 2, that's 4. So of the 8, we have to minus 4. That gives us 4 electrons remaining. Now, where are we going to put them? Are we going to put the electrons on the hydrogens? No, the hydrogens already have 2 electrons, so they're done. This oxygen only has 4, though, and it needs to have 8. So we'll put 2 here and 2 here. This is our water molecule. Hydrogen has a duet, hydrogen has a duet, oxygen has an octet, 2, 4, 6, 8, and the total is 8. This is our valid Lewis structure. Now, one thing I do want to mention is the way that I'm drawing these on the page is not exactly how they are in real life. Like this looks like it's flat, like a plus sign, and these are 90 degrees from each other. As you'll see in our next video, these are actually going to be more than 90 degrees apart. When you sort of lift it up off the page and you're thinking in 3 dimensions, it has a shape like a tetrahedron. And water is not. This makes water look linear, like a straight line. It actually has sort of a bent or like a V shape. Okay, so the only way that this Lewis structure, in terms of the way the shape is drawn, would make sense is if you were underneath the water molecule looking up at it, as opposed to looking at it from the side. If you looked at it from the side, it might look more like that, like bent or V-shaped. And you'll find out more why in our upcoming videos about shapes of molecules. Let's do some more practice. And these ones are meant to get, we just did those 4. Those are about as easy as it gets. Okay, those are about as easy as it gets. And these are meant to be, slowly getting a little bit more challenging as you go. Okay, so if you want to pause the video and try to solve these, go for it. I'm going to work through them in just a moment. Okay, here we go. Step 1, count the total number of valence electrons. So, Si it's in column 4A, so it has 4 valence electrons. And oxygen is in column 6A, so it has 6 valence electrons, and we have 2 of them. So 6 times 2 is 12, plus 4, that's 16 electrons, valence electrons, 16 of them. So we'll put Si here at the center, and then we'll put an O here and an O here. We're going to connect them with single bonds. Each bond counts as 2, so that's 2 and that's 4. So we've used up now 4, and that leaves us with 12 electrons left. So we need to make it so that this has 8, this has 8, and this has 8. And just to give you an idea, you might say, all right, well, we have 12. I'm going to bring in a pencil here. You might have 12, so you say, okay, well, we'll put 6 on this oxygen and 6 on this oxygen. Now, this oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8, and the total number is 2, 4, 6, 8, 10, 12, 14, 16, right? So we're good to go? Not so much, because look at silicon. It only has 4. It doesn't have a valid octet. And so then you say, oh, it needs to have more, so maybe we'll take some off of this and put it on here, and maybe we'll take some off of this and put them on here. Right? There, now Si has 8, right? 2, 4, 6, 8. But look at oxygen, 2, 4, 6, 2, 4, 6. So it seems like we can't get them all to have octets, right? Or if you said, well, why don't we just put more here and put more here, right? Now oxygen has 2, 4, 6, 8. Silicon has 2, 4, 6, 8, and oxygen has 2, 4, 6, 8. They all have 8, right? So now is it correct? Well, if you count the total number of valence electrons, it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Do we have 20 electrons? No. So this is wrong. So you might be saying, hold on a second, Mr. Rosen. The only way to have octets is to have too many electrons. And that is where you're incorrect. And this introduces the concept of a double bond. Or, if you want to take it even further, a triple bond. Okay? If you get to a situation where you cannot form a valid Lewis structure, meaning all of your octets are fulfilled, and it has the correct total number of valence electrons using single bonds, that means you might need to use one or more double bonds. So watch this. Instead of a single bond, I'm going to have a double bond. Look at that Lewis structure. Oxygen, 2, 4, 6, 8. Silicon, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. All of them have 8, so octets are fulfilled. And count the total number of valence electrons, 2, 4, 6, 8, 10, 12, 14, 16. Ding, 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 ding. Valid Lewis structure. Okay, so if you use single bonds and you cannot make it so that all of your octets are fulfilled and you still have the correct number of valence electrons, then that means you probably need a double bond or maybe multiple double bonds or a triple bond. Let's continue along. Carbon has 4 electrons. Hydrogen has 1, and there are 2 of them, so that's 2 electrons. And oxygen has 6 electrons. So 2 plus 4 is 6, plus 6 is 12 valence electrons. We're going to place carbon at the center. Remember, hydrogen can only form a single bond, so we're going to have a hydrogen, we're going to have a hydrogen, and then we're going to have an oxygen. You just sort of space them out as much as you can around the central atom. We're going to connect it with single bonds. Each bond represents 2 electrons, so we've used up 6 of these, and we have 6 left. Now, the hydrogens only need 2 electrons, so these are done. Okay, the hydrogens are done. But carbon needs to have 8, and oxygen needs to have 8. Now, if we have 6 here, you could put 2, 4, 6 on this oxygen, and that give it 8, but the carbon would not have 8. Right? If I put the 6 remaining on oxygen, it would give oxygen 8, but carbon would still not have 8. The only way to make this work is to have a double bond between these two. Putting a double bond there makes it so that your hydrogens still have duets. Carbon now has 2, 4, 6, 8. And then you used up 2 of these. You place the remaining 4 on oxygen. So if you look at this Lewis structure, oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And the hydrogens each have 2. So all octets and duets are fulfilled. And count the total number of valence electrons. 2, 4, 6, 8, 10, 12. Ta-da! Valid Lewis structure. We continue along. Nitrogen is in column 5A. So that's 5 electrons times 2, which is 10. Plus we have 4 hydrogens. Each hydrogen is 1, so that's 4 electrons. So 10 plus 4 is 14 valence electrons. We're going to have nitrogen. We're going to have another nitrogen. And 4 hydrogens. So I'm going to put a hydrogen over here and a hydrogen over here. Hydrogen over here, hydrogen over here. And I'm going to connect them using single bonds. So single bond, single bond, single bond, single bond. We'll start with this, and then I guess I'll put 1 here too. So that's a molecule. We just connected everything with a single bond. This is 2, 4, 6, 8, 10. 10 of the 14. So we have 4 left. The hydrogens only need to have a single bond and they're done. So that's done, that's done, that's done, that's done. But right now this nitrogen has 6 and it needs to have 8. And this nitrogen also needs to have 8. So fortunately we have 4, which means we could put 2 electrons on this nitrogen and 2 electrons on this nitrogen. If you do that, nitrogen has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8. The hydrogens all have their duets, and the total is 2, 4, 6, 8, 10, 12, 14. Ta-da! Valid Lewis structure. Hopefully you're starting to get the hang of this. They're meant to be getting more complicated as we progress. Next one, C2Br2. Carbon has 4 valence electrons, so 4 times 2 is 8. And then bromine is underneath chlorine, which is underneath fluorine. It has 7 valence electrons. It's in column 7A. So that's going to be 7 times 2. So we have 8 and we have 14. And we're going to add those together. And we get 22 electrons. 22 valence electrons. We have 2 carbons and 2 bromines. I'm going to put a carbon and then I didn't actually I don't actually know if this is going to be experimentally what it really is. I think it might actually be just a BR on each end rather than like this. But we'll see if we can get a valid Lewis structure. So we'll put a bond here, a bond here, a bond here. That would be 6, which leaves us with 16, 6, 6. Yeah, this is, I might not be setting this one up right. Sorry, folks. Let's see here. B, R, C, C, B, R. So, as I was drawing this, I've never done this molecule before. I just pulled it off the internet. But basically, when I started drawing it this way, I realized in terms of the number of bonds the carbon would form and the lone pairs, it just sort of, it would never happen like that. So here I have 2 carbons and a bromines on each side of it. Okay, now I started by connecting them all with single bonds, and then I put 6 valence electrons around bromine and 6 around this bromine. So if you look at this, bromine has 2, 4, 6, 8. Bromine has 2, 4, 6, 8. This carbon has 2, 4, 6, 8, and this carbon has 2, 4, 6, 8. So they all have 8, they all have octets, and the total number needs to be 22. This has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So this is a valid Lewis structure for both. And sometimes you have to do kind of what I just did, is I started setting it up one way and said, oh, well, that's actually not going to work. I knew pretty quickly it wasn't going to work out. But this is the Lewis structure for that, and it has a triple bond. And that's kind of the only way that you can make it work with this number of valence electrons and still have your octets. Now, the last two I want to mention that they both have charges. Okay, they're both ions. When you have an ion, that means that it has either gained additional electrons or lost electrons. You need to take that into consideration when you're counting the total number of valence electrons that you have. So chlorine has 7 valence electrons. Oxygen has 6 valence electrons. And we have 3 of them. So 6 times 3 is 18. 18 plus 5 is 25. Now, that would be ClO3. Sorry, my thumb's just kind of in the way, but just ClO3 would give you 25 electrons. But this has a minus charge. So that means that overall, it has an additional electron. So neutral ClO3 would be 25. If it's ClO3 with a minus charge, that means it has an additional electron. So you have to say 25 plus 1, which is 26 valence electrons. So neutral ClO3 would be 25. ClO3 with a negative charge means it has an additional electron. So you need to take that into account. All right, I'm going to put chlorine here, and then I have oxygen, oxygen, oxygen. I'm going to connect them starting with single bonds. Each bond is 2, so that's used up 6 of these, leaving me with 20. I'm going to put 6 on each oxygen. That's used up 18, and there are 2 remaining. Those 2 are going to go on the chlorine. They all have 8, and the total is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Now, one final thing I want to mention, if it's an ion, if it has a charge, you put the Lewis structure in square brackets, and then you denote the charge outside of the bracket. And that tells you that this Lewis structure has an overall charge. So let's do sort of the same thing on the next problem. P has 5 valence electrons. Oxygen has 6. 6 times 4 is 24. So if we just did P plus our 4 oxygens, that would give you 29 electrons. But it has a -3 charge. So just PO4 is 29. But -3 means it has 3 additional electrons. So you actually do 29 plus 3 to get 32 electrons, valence electrons. That's what you're going to use to draw your Lewis structure. So we're going to have P, we're going to have O, 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 and O. Connect them using single bonds. Each bond is 2 electrons, so we've used up 8 of the 32, and we have 24 left. And hopefully you recognize there are 4 oxygens. We could put 6 on each of them, and 6 times 4 is 24. That will work out perfectly. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So now all the oxygens have 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and phosphorus has 2, 4, 6, 8, right? All octets are fulfilled, and the total is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Ding, ding, ding. Valid Lewis structure. Okay, and again, final thing, this has a charge, so we have to put the whole Lewis structure in square brackets and denote the charge, which is -3 outside of the square brackets. Okay? This is drawing Lewis structures. We started with the most simple examples and worked our way to, double bonds, even triple bonds, and then ions, which you have to take the electrons into account. A couple of big ideas from our practice. A single bond is 2 shared electrons, okay, which is an electron pair. A double bond is 2 electron pairs, so 4 total shared electrons, and a triple bond is 6 electrons being shared. If you have an ion, you need to draw its Lewis structure in square brackets with the charge written in the upper right corner. You need to add or subtract the appropriate number of electrons from the total number of valence electrons, depending on the charge. So, as is always the case, the more you do, the more comfortable you get, and the faster you get at drawing Lewis structures. It's important to be able to draw valid Lewis structures because we're going to use those Lewis structures to correctly predict the shape of the molecule, and the shape of the molecule is crucial in terms of predicting properties of the substance. Things like boiling point, melting point, vapor pressure, physical properties of the substance. And you're going to learn all about that in the coming weeks and videos. So, good job. Keep up the hard work. Let me know if you need anything. This is Mr. Rosen. Out.